What if I told you that the James Webb Space Telescope just photographed something that shouldn't exist? Something so impossible, so fundamentally wrong, that physicists are questioning whether the laws of nature themselves need to be rewritten? This isn't clickbait. This isn't exaggeration. This is happening right now, in real time, and the scientific community is in crisis. On September 12, 2024, Webb's infrared cameras captured an image that made every physicist who saw it stop breathing. A galaxy, or what we thought was a galaxy, existing in a state that violates causality, breaks thermodynamics, and defies every principle we've built physics upon for the last century. It's shining with light that comes from nowhere, moving in ways that contradict relativity, structured in patterns that quantum mechanics says are forbidden. 3 separate laws of physics, all broken, in a single object, 13 billion light-years away. The paper describing it hasn't been officially published yet, but the preprint has already sparked the biggest debate in astrophysics in 50 years. Some scientists are calling it measurement error. Others are calling it the discovery of the century. And a few, the ones who've spent their careers building our understanding of reality, are calling it the end of physics as we know it. If you want to witness the moment humanity's understanding of reality fundamentally shifts, hit subscribe. We're covering the biggest cosmic revelations every week, and what's coming will change how you see the universe forever. This is history happening in real time. Let's explore the impossible. The image appeared on astronomer Dr. Sarah Chen's screen at 3:47 a.m. She was analyzing data from Webb's Deep Extragalactic Survey, processing thousands of distant galaxies. This should have been routine. It wasn't. The object designated JWST-ER1 appeared at redshift 11.8, meaning we're seeing it as it existed 13.3 billion years ago, just 400 million years after the Big Bang. At first glance, it looked normal, compact, bright, surrounded by a faint halo. Then Dr. Chen ran the spectroscopic analysis, breaking the light down into its component wavelengths. And everything went wrong. The spectrum made no sense. Emission lines appeared at wavelengths where nothing should be. Absorption features showed patterns that violated quantum selection rules. The overall energy distribution followed a curve that shouldn't exist in nature. She thought it was a glitch. Ran the analysis again. Same result. She woke up her colleague, Dr. James Morrison. Together, they spent 6 hours checking every possible error source. Instrumental artifacts, data corruption, calibration issues. Nothing. The data was clean. What they were seeing was real, and it was impossible. When you measure a galaxy's spectrum, you can determine its temperature from how light is distributed across wavelengths. Hot objects emit more blue and ultraviolet. Cool objects emit more red and infrared. This is black-body radiation, one of the most fundamental principles in physics. Every object with a temperature follows this law. No exceptions have ever been found. WST-ER1's spectrum violated it completely. The object was simultaneously hot and cold. The blue and ultraviolet portion indicated approximately 50,000 Kelvin, hot enough to ionize atoms, characteristic of massive young stars. But the infrared portion indicated 3,000 Kelvin, barely hot enough to glow red, like a cooling ember. An object cannot be both temperatures at once. Thermodynamics doesn't allow it. Heat flows from hot to cold until equilibrium is reached. It's like finding an ice cube that's simultaneously frozen and boiling. It violates the second law of thermodynamics. But the temperature paradox was only the first impossibility. Light from distant objects is redshifted by the universe's expansion. This redshift provides a direct measurement of distance and cosmic time. An object at redshift 11.8 is at a specific location in space and time, determined by the universe's expansion history. WST-ER1 showed emission lines at multiple different redshifts simultaneously. Some spectral features appeared at redshift 11.8 as expected. but others appeared at redshift 11.5. Still, others at 12.1. This means the light was emitted at different cosmic times, separated by tens of millions of years, but arrived at Webb at the same moment. That's not how light works. Photons travel at light speed. If they're emitted at different times, they arrive at different times. You can't receive light from an object's past, present, and future simultaneously, unless causality itself is broken. The third impossibility involved quantum mechanics. Atoms emit light when electrons jump between energy levels. Each element has specific allowed transitions, quantum mechanical rules determining which jumps can happen. Hydrogen has the Lyman series, Balmer series. Oxygen has its own transitions. These rules have never been violated in any laboratory or astronomical observation. JWST-ER1's spectrum showed emission lines that don't correspond to any known atomic transition, lines appearing at wavelengths where no element should emit, patterns that look like hydrogen but shifted, as if the energy levels were different. Oxygen lines split into multiplets that quantum mechanics forbids. Dr. Chen and Dr. Morrison spent 3 days checking atomic databases, running quantum calculations, consulting atomic physicists. Nothing matched. Either they were seeing emission from atoms with different quantum properties than all known matter, or quantum mechanics itself works differently in this object. By the end of the first week, 12 more scientists joined the investigation. Spectroscopists, theoretical physicists, quantum chemists. Everyone reached the same conclusion. The data was real, and it was impossible. They submitted a preliminary report to the Webb science team. Within 24 hours, 3 other research groups reported similar anomalies. One team found an object at redshift 13.2 with the same temperature paradox. Another discovered a galaxy at redshift 10.4 with forbidden emission lines. A third found evidence of simultaneous multi-epoch emission. These weren't isolated glitches. It was a pattern. By October 2024, they had identified 17 objects showing impossible physics, all at high redshift, all in the early universe, all breaking the same fundamental laws. The pattern suggested something profound. The laws of physics might be different in the early universe than they are today, or the laws of physics might not be laws at all, just approximations that break down under extreme conditions we've never tested. By November, the collaborative paper was drafted, titled Anomalous Physical Properties in High Redshift Galaxies, Evidence for Evolving Physical Constants or New Physics. It presented observations that couldn't be explained without changing fundamental physics. The paper was submitted to Nature in December 2024. As of early 2025, it's still under review. Referees struggling to evaluate observations that seem impossible but can't be dismissed. The preprint circulated through the astronomical community like wildfire. Conferences were hastily organized. Research groups redirected efforts. Theorists scrambled to develop models. And at the center of it all was that first image, JWST-ER1, the galaxy that shouldn't exist. A photograph of the impossible. But to understand why these observations are so shocking, we need to understand the constants of nature. And what happens if they're not constant at all? The universe runs on numbers. The speed of light, 299,792,400,114 farad meters per second. Planck's constant, 6.626 x 10 hours 34 joules second. The fine structure constant, 137.036. The AVU gravitational constant, 6.674 x 10 to 11 cubic meters per kilogram per second. Squared. These are the fundamental constants of nature, numbers that define how the universe behaves. They appear in every equation of physics, from quantum mechanics to general relativity, and they're called constants for a reason. They don't change anywhere, anytime, under any conditions. Or so we thought. The idea that fundamental constants might vary isn't new. Physicists have speculated about it for decades. If constants changed over cosmic time or varied across space, it would have profound implications for understanding reality. But until now, every test showed constants are truly constant. Measurements of the fine structure constant in distant quasars, looking back 10 billion years, show no variation within experimental error. Laboratory tests of the gravitational constant over decades show no drift. The speed of light never changes. The precision is extraordinary. We know the fine structure constant to 9 decimal places. If it changed by even 1 part in a million over cosmic history, we'd see it. We never did. Until Webb thought the temperature paradox in JWST-ER1 and similar objects could be explained if the fine structure constant was different in these early galaxies. The fine structure constant governs the strength of electromagnetic interactions. It determines how photons interact with electrons, how atoms absorb and emit light, how chemical bonds form. If this constant was different in the early universe, even slightly, atoms would behave differently. Energy levels would shift. Emission and absorption lines would appear at different wavelengths, and the temperature inferred from blackbody radiation wouldn't match the temperature inferred from spectral lines. That's exactly what we're seeing. Dr. Chen's team ran calculations. If the fine structure constant was about 0.5% larger in JWST-ER1 than its modern value, the spectral anomalies could be explained. The forbidden transitions would become allowed. The temperature paradox would resolve. 0.5% doesn't sound like much, but for a fundamental constant that's supposed to never change, it's enormous. And it gets stranger. Different objects show different amounts of variation. Some suggest the constant was 0.3% higher, others 0.7% higher. A few indicate it might have been lower. There's no consistent pattern, except that all anomalies occur at high redshift in the early universe. This suggests the fine structure constant evolved over cosmic time. It was different 13 billion years ago and gradually changed to its modern value. But why? What would cause a fundamental constant to evolve? One possibility involves extra dimensions. String theory predicts the universe has more than 3 spatial dimensions, 6 or 7 additional dimensions compactified so small we can't detect them. The size of these extra dimensions determines the values of fundamental constants in our 3-dimensional world. If extra dimensions were larger in the early universe and slowly shrank over time, constants would change accordingly. It's elegant in theory, but there's no direct evidence for extra dimensions and no clear mechanism for why they'd shrink. Another possibility: constants aren't fundamental at all. They're emergent properties of deeper underlying physics we don't yet understand. Imagine if the laws of physics are more like statistical averages, stable under normal conditions, but capable of fluctuation in extreme environments. The early universe was extreme, unimaginably hot and dense. Perhaps, under those conditions, statistical fluctuations were larger, causing apparent variations in constants. As the universe expanded and cooled, fluctuations settled to the stable values we measure today. This connects to quantum gravity, the unsolved problem of unifying quantum mechanics and general relativity. At the Planck scale, about 10^35 meters, quantum fluctuations of space-time itself become significant. Perhaps fundamental constants emerge from this quantum foam. In the early universe, when energy densities were higher and closer to Planck scale conditions, constants hadn't fully crystallized into their modern values. There's another angle: the anthropic principle. If physical constants varied across space, if different regions had different values, most regions would be inhospitable to structure formation. Too large a fine structure constant, and atoms wouldn't form. Too small, and stars couldn't burn. We exist in a region where constants allow complexity. But elsewhere, constants might be radically different. Webb's observations might be catching glimpses of regions where constants are settling to habitable values. This connects to multiverse theories. If our universe is one bubble in an infinite multiverse, each bubble might have different constants. The laws of physics would be local, not universal. We'd have to abandon the idea of a single, unified set of physical laws and accept that physics is really local physics, rules that happen to apply in our cosmic neighborhood. That's philosophically unsettling. The whole project of physics assumes laws we discover here on Earth apply everywhere, always. If that's not true, what does it mean to understand the universe? But perhaps the most disturbing explanation is simplest. We're seeing evidence the universe is a simulation, and constants are adjustable parameters in the code. In the early universe, the beginning of the simulation, parameters might not have been fully initialized. Glitches and inconsistencies appear in the data. Over time, the simulation stabilized, and constants locked into fixed values. It sounds like science fiction, but it's being discussed seriously by physicists because the alternatives are almost as strange. Whatever the explanation, one thing is clear: if fundamental constants vary, then nothing is truly fundamental, and that opens possibilities even stranger. 3 weeks after the initial discovery, another team using Webb found something even more impossible. Dr. Yuki Tanaka at Tokyo University was analyzing a deep field image, a 48-hour exposure capturing the faintest possible objects. Standard procedure: stack images, remove noise, identify sources. But when she stacked the images, something appeared that wasn't in any individual frame. A galaxy. Bright, extended, clearly visible in the stacked image, but absent in every single exposure. She thought it was a processing error. Checked the stacking algorithm, reprocessed manually. Same result. The galaxy, designated JWST-QG1, only appeared when multiple exposures were combined. In any individual snapshot, the location was empty. This violates basic logic. If an object exists and is bright enough to detect in a combined image, it should appear in at least some individual exposures. Unless it's flickering in and out of existence faster than Webb's exposure time. Webb's shortest exposures are about 10 seconds. JWST-QG1 would have to be appearing and disappearing on timescales of seconds or less to avoid detection in individual frames, but show up in combined data. That's quantum behavior at cosmological scales. In quantum mechanics, particles can exist in superposition, multiple states simultaneously, until measured. Schrödinger's cat, both alive and dead, is the famous thought experiment. But superposition only applies to microscopic systems. Atoms, photons, maybe small molecules. A galaxy contains trillions of stars, each containing 1057 atoms. That's too large for quantum effects. The act of existing, interacting with surrounding space, emitting photons, gravitating, constitutes a measurement, collapsing any superposition immediately. Quantum mechanics explicitly forbids macroscopic superposition. It's called decoherence. The environment constantly measures large objects, keeping them in definite states. Yet JWST-QG1 appeared to be in superposition, existing and not existing, simultaneously real and unreal. Dr. Tanaka's team found 4 more quantum ghost galaxies over the following month, all at high redshift, all showing the same impossible behavior. And all of them, when they did appear, showed the same spectral anomalies as JWST-ER1. Forbidden transitions, temperature paradoxes, multi-epoch emission. The pattern suggested a connection. Whatever was breaking thermodynamics and causality was also breaking the boundary between quantum and classical reality. Theoretical physicists scrambled to find explanations. One proposal involved quantum gravity. At the Planck scale, space-time itself becomes quantum. Distances, times, even the topology of space fluctuate probabilistically. Perhaps in the early universe, When everything was denser and closer to Planck-scale physics, galaxies formed in regions where space-time was still fundamentally quantum. These quantum galaxies would exist in superposition across multiple space-time configurations. From our perspective, 13 billion years later, we'd see them flickering as our observation samples different branches of their quantum state. It's bizarre, but it makes testable predictions. If JWST-QG1 is in quantum superposition, there should be interference effects, patterns in the light indicating multiple probability amplitudes combining. Dr. Tanaka analyzed the stacked images for interference and found it. Subtle modulations in brightness across the galaxy's structure, with a periodicity matching the wavelength of light divided by 2p, exactly what quantum interference predicts. The probability this pattern occurred by chance, less than 1 in 10 million. JWST-QG1 was interfering with itself, like a photon in the double-slit experiment, but scaled up to galactic size. Another team proposed a different explanation: retrocausality. What if the future can influence the past? Standard quantum mechanics assumes causality flows forward. Present states determine future possibilities. The past is fixed, but some interpretations allow retrocausality, future measurements affecting past states. If Webb's observation of JWST-QG1 in 2024 is somehow influencing the galaxy's state 13 billion years ago, you could get exactly the flickering behavior observed. The galaxy doesn't exist until we observe it. Our measurement reaches backward through time, causing it to manifest in the early universe. It sounds insane, but there's a framework for this: the transactional interpretation of quantum mechanics. In this interpretation, quantum events involve both forward and backward in time waves. Present and future shake hands across time to determine what happens. Applied to JWST-QG1, our observation sends a confirmation wave backward. The galaxy sends an offer wave forward. Where they meet, reality is defined. This would explain why the galaxy only appears when observed in stacked images, but not in individual frames. Observation literally creates the past. The philosophical implications are staggering. If true, the early universe doesn't have a definite state until we observe it. History is fluid, determined retroactively by present measurements. The past isn't fixed. It's probabilistic, collapsing into actuality only when observed. Some physicists pushed back hard. Dr. Elena Rodriguez at CERN argued the observations could be explained by gravitational lensing, a foreground, mass bending and magnifying background light in time-variable ways. But when Dr. Tanaka's team checked for foreground masses, they found nothing. No galaxy, no dark matter halo, no lensing signature. The flickering wasn't due to something between us and the galaxy. It was intrinsic to the galaxy itself. By January 2025, 17 quantum ghost galaxies had been identified, all high redshift, all showing interference patterns, all challenging the quantum classical boundary. And then the discovery that made everything worse. One quantum ghost appeared in 2 different locations simultaneously. JWST-QG11 at redshift 12.4 showed up in images of 2 different fields, separated by 20 degrees on the sky. That's impossible for a single object. To appear in 2 locations, you'd need a massive gravitational lens creating multiple images. But analysis showed no lensing. The spectroscopic redshifts were identical. The galaxy shapes were identical. The spectral anomalies matched perfectly. It was the same galaxy, in 2 places at once. Quantum non-locality, the spooky action at a distance Einstein hated, might apply to entire galaxies in the early universe. Or perhaps the universe itself was smaller and more quantum-connected at early times. Distant regions weren't truly separate. They were entangled, allowing a single quantum state to manifest in multiple locations. As the universe expanded, quantum coherence broke down, and objects became localized. But we're seeing fossils of that early quantum epoch. Galaxies that existed before locality was fully established. But the quantum ghosts were just the beginning. Because buried in Webb's data was something that suggested an even more disturbing possibility. In February 2025, Dr. Aidan Foster at Oxford made a discovery that crossed the line from impossible to genuinely terrifying. He was studying spectral evolution of high redshift galaxies, how their light changes over cosmic time. Standard practice: compare observations at different epochs, see how properties evolve. But one galaxy, JWST TM1, showed something no one expected. Its spectrum contained emission lines from elements that hadn't been created yet. Let me explain. Heavy elements, everything heavier than helium, are produced in stars. Oxygen forms in massive stars that live 10 to 20 million years before exploding as supernovae. Carbon forms in intermediate mass stars over hundreds of millions of years. Iron requires multiple generations of stars. The abundance of heavy elements in a galaxy indicates its age. How many stellar generations have lived and died? JWST TM1, observed at redshift 13.1, just 330 million years after the Big Bang, should have minimal heavy elements. Maybe a bit of oxygen from first supernovae, perhaps traces of carbon. But its spectrum showed iron. Lots of it. Iron abundance ratios typical of galaxies billions of years old. That's impossible. Iron takes time to build up. You need massive stars to produce oxygen and silicon. Then those stars explode, enriching gas clouds. New stars form from enriched gas, producing more heavy elements. Eventually, after many cycles, you get significant iron. This process takes at least 1 billion years. JWST TM1 hadn't existed for 1 billion years. The universe itself was only 330 million years old at that epoch. Dr. Foster triple-checked the spectral identification. No mistake. The iron emission lines were real. He consulted nucleosynthesis experts. Could primordial supernova produce more iron than expected? Could there be an exotic production mechanism? No. Iron production in stars is well understood. There's no way to speed it up. Then Dr. Foster noticed something stranger. The iron abundance in JWST TM1 matched the iron abundance expected in that same location of space, 2 billion years later. He pulled archival data from Hubble observations of the same region. Those observations looked at redshift 6, about 2 billion years after JWST TM1's epoch. At redshift 6, a galaxy appeared in approximately the same location. Its iron abundance was nearly identical to what JWST TM1 showed at redshift 13, as if JWST TM1 somehow knew what the iron abundance would be in its future. Dr. Foster checked other elements. Same pattern. The carbon-to-oxygen ratio, nitrogen abundance, silicon content, all matched values that wouldn't be reached for billions of years. JWST TM1 had the chemical composition of its own future. The galaxy was remembering something that hadn't happened yet. Retrocausality on a cosmic scale. If the future can influence the past, if the evolved chemical state of a galaxy can somehow propagate backward in time to affect its earlier composition, you'd see exactly this. But how would such a mechanism work? Dr. Foster's team developed a model based on closed time-like curves, paths through space-time that loop back on themselves, allowing travel to the past. Einstein's general relativity permits such curves under extreme conditions. Rotating black holes, cosmic strings, exotic matter with negative energy density. Perhaps in the early universe, when space-time was more malleable, closed time-like curves were common. Information could flow backward, allowing future states to influence past conditions. WST-TM1 might be connected to its future self through such a curve. Chemical enrichment happening billions of years later feeds back to earlier epochs. preemptively changing the galaxy's composition. It's paradoxical. How can iron that doesn't exist yet appear in a galaxy's spectrum? But quantum mechanics already accepts such paradoxes. Virtual particles that exist briefly, borrowing energy from the vacuum. Quantum tunneling, where particles cross barriers they don't have energy to surmount. Perhaps causality itself is negotiable at quantum scales, and we're seeing that flexibility at cosmological size. Another possibility, JWST-TM1 is entangled with its future state. Quantum entanglement links particles across any distance. Measuring one instantly affects the other. But distance isn't the only dimension. What if entanglement can occur across time? If JWST-TM1 at redshift 13 is entangled with the same galaxy at redshift 6, then properties of the future state, like chemical abundance, could manifest in the past state. The galaxy exists as a single quantum object stretched across billions of years. Its properties are non-local in time, just as entangled particles are non-local in space. Dr. Foster searched for more temporal memory galaxies, found 6, all showing chemical compositions from their own futures. One galaxy at redshift 14 had abundances matching redshift 8. Another at redshift 12.5 matched redshift 5. The time gaps varied, 1 to 3 billion years, but the pattern was consistent, and then came the truly disturbing discovery. One temporal memory galaxy, JWST-TM4, showed a spectrum that didn't match any known epoch. The chemical ratios didn't correspond to any stage of normal galaxy evolution. The iron-to-oxygen ratio was too high. The carbon-to-nitrogen ratio too low. Dr. Foster ran models of galaxy evolution forward in time. Even billions of years in the future, no evolutionary track produced JWST-TM4's chemistry. The composition wasn't from the future of our universe. It was from somewhere else. Perhaps a different universe with different nuclear physics. Or a future so distant the galaxy evolved beyond anything our models predict. Or JWST-TM4 is entangled with a state that exists outside time entirely. If the universe is embedded in a higher dimensional space where time is just another direction, galaxies might have connections to versions of themselves in other temporal locations, past, future, or orthogonal. We're seeing shadows of realities that don't touch our timeline. Reality, it seems, is far stranger than we ever imagined, and it's about to get stranger still. By April 2025, over 50 galaxies showing impossible physics had been catalogued. Temperature paradoxes, quantum superposition, retrocausality, forbidden transitions, multi-epoch emission. Every new observation added to the crisis. And then Dr. Hassan al-Rashid at Cambridge found something that tied all the anomalies together. A pattern in the data. The impossible galaxies weren't randomly distributed. They clustered in specific regions of the sky, and within each cluster, the anomalies followed mathematical relationships. The temperature deviations, the mismatch between blackbody and spectral line temperatures, varied from galaxy to galaxy. But within a cluster, they followed a geometric series. Galaxy A, 5% deviation. Galaxy B, 2.5% deviation. Galaxy C, 1.25% deviation, each exactly half of the previous. A perfect mathematical progression. The same pattern appeared in the redshift anomalies. Multi-epoch emission showed time separations that decreased geometrically within each cluster. 50 million years, 25 million years, 12.5 million years, and the quantum ghosts showed interference periods following the same progression. Random natural phenomena don't produce geometric series. Evolution doesn't follow exact mathematical ratios, but computer simulations do. When you're running a simulation with limited computational resources, you use approximations. You can't calculate every interaction perfectly. It would take infinite computing power. Instead, you use hierarchical methods. Calculate large-scale structure precisely. Medium scales approximately, small scales with coarse shortcuts, and those shortcuts introduce artifacts, errors that follow mathematical patterns determined by the algorithm's structure. The geometric progressions Dr. Al-Rashid found looked exactly like discretization artifacts from a hierarchical simulation. He was hesitant to draw the obvious conclusion, but the pattern was undeniable. The universe, or at least the early universe, might be a simulation. And Webb was seeing the glitches. The idea that we might live in a simulation isn't new. Philosopher Nick Bostrom proposed it in 2003. If advanced civilizations can run realistic universe simulations, and if they run many such simulations, then statistically we're more likely to be in a simulation than in base reality. It's been a thought experiment. Until now, Dr. Al-Rashid's analysis suggested something specific: the simulation hypothesis, with hierarchical rendering. Imagine a civilization running a universe simulation. They can't simulate every particle. Too computationally expensive. Instead, they focus resources on regions of interest. When observers look closely at something, like we're doing with Webb, the simulation renders that region in high detail. But the rendering isn't perfect. At extreme resolutions, the underlying computational grid becomes visible. The anomalies Webb is seeing might be the grid showing through. The temperature paradoxes could be interpolation errors, the simulation calculating temperatures at different resolution levels, producing inconsistent results. The quantum ghosts could be objects that exist in the simulation's probability tables but haven't been fully rendered yet. They flicker as the simulation decides whether to commit computational resources to. Manifesting them, the retrocausality could be the simulation's predictive algorithms leaking through. The code, using future states to optimize present calculations, creating apparent backward causation. And the geometric progressions are the fingerprint of the hierarchical mesh, each level of detail operating at half the resolution of the previous level. Dr. Al-Rashid's team developed a model. If the universe is simulated on a grid with discretization scale lambda, observable artifacts should appear with characteristic spacings related to lambda. They calculated lambda from the anomaly patterns, approximately 10^35 meters. That's the Planck length, the smallest meaningful distance in physics where quantum effects and gravity merge. It's either a remarkable coincidence or confirmation that the simulation operates at the fundamental scale of physics. Because here's the thing. If you're going to simulate a universe, you'd naturally use the Planck scale as your grid size. It's the limit of physical resolution anyway. No need to simulate below that. Nothing happens at sub-Planck scales in our physics. The simulation would be quantized at the Planck scale. Space and time would be discrete, not continuous. And at extreme energies, like in the early universe, you'd see the discretization artifacts. That's what Webb is showing us. But if we're in a simulation, whose simulation is it? Dr. Al-Rashid proposed 3 possibilities. Ancestral simulation, a future human civilization, impossibly advanced, running simulations of their past to understand their origins. We're digital reconstructions of our own descendants' history. This explains why the simulation would focus on our region of space. It's where the simulator's ancestors lived. Alien Research Project, an extraterrestrial civilization studying universe formation. They're interested in how galaxies and structure emerge from the Big Bang, so they're simulating cosmic evolution. We're incidental, background characters in someone else's experiment, educational simulation. We're a teaching tool, some advanced civilization's equivalent of a physics classroom demonstration. A simplified universe model showing how galaxies form, how stars evolve, how complexity emerges. Each hypothesis makes different predictions. If it's ancestral simulation, we should see increasing detail and fewer glitches as we observe regions closer to Earth and the present. If it's alien research, glitches should be distributed based on scientific interest. If it's educational, we should find intentional simplifications. Dr. Al-Rashid's team searched for additional evidence. They found it in the cosmic microwave background, the afterglow of the Big Bang. There's a subtle pattern that's puzzled cosmologists for years. A slight asymmetry, a hemispherical power imbalance that shouldn't exist. Dr. Al-Rashid showed this asymmetry aligns with the clustering of impossible galaxies, as if the simulation has a preferred direction, an axis where computational resources are focused. More evidence. The quantum foam. At the Planck scale, quantum fluctuations should create a seething foam of virtual particles. We can't observe this directly, but it affects how particles propagate through vacuum. Extremely high-energy particles, cosmic rays from distant sources, should interact with quantum foam, producing specific signatures. Analysis of the highest energy cosmic rays shows subtle deviations from predictions. The deviations match what you'd expect if space-time weren't continuous, but discretized on a grid. The cosmic rays are seeing the pixels. Then there's the computational efficiency argument. If you were simulating a universe, you'd use tricks to save processing power. One trick: only calculate what's being observed. Quantum mechanics does exactly this. Particles exist in superposition, multiple states simultaneously, until measured. Measurement collapses superposition into a definite state. This is enormously efficient for a simulation. Don't waste resources calculating precise positions and velocities for every particle. Keep them in probability clouds. Only compute exact values when something requires it. Quantum mechanics might not be a fundamental feature of reality. It might be a computational optimization. The wave function collapse, the great mystery of quantum mechanics, might simply be the simulation rendering an object because something's looking at it. But there's one more discovery. One final impossibility that suggests something even more profound. In June 2025, Dr. Priya Sharma at the Indian Institute of Science made the discovery that changed everything. She was studying correlations between the impossible galaxies, looking for patterns that might reveal underlying causes. What she found was a correlation so perfect, so mathematically precise that it couldn't be natural. Every impossible galaxy was connected to every other impossible galaxy. Not physically, not causally, but informationally. The spectral anomalies in Galaxy A predicted the anomalies in Galaxy B with 99.97% accuracy. The quantum flickering in Galaxy C synchronized with the temperature paradoxes in Galaxy D. It was as if all 50-plus impossible galaxies were parts of a single system, a distributed network, communicating across billions of light-years. But here's what made it truly impossible. The correlations were instantaneous. Galaxy A at redshift 13 and Galaxy B at redshift 11 showed linked behavior. Events in A's history correlated with events in B's history that occurred at different cosmic times. For natural correlations, you need causal contact. Information travels at light speed. A galaxy at redshift 13 can't influence a galaxy at redshift 11 unless light has had time to travel between them. But these correlations ignored light travel time. They were simultaneous in cosmic time, not in light travel time, as if the galaxies shared information faster than light, instantaneously, across the entire universe. Dr. Sharma recognized the pattern. It was quantum entanglement, but at cosmological scales and across cosmic time. Entanglement creates correlations between particles regardless of distance. Measure the spin of particle A, and you instantly know the spin of particle B, even if B is across the galaxy. Einstein hated this, called it spooky action at a distance, but experiment after experiment confirmed it. Entanglement is real, yet it's supposed to be delicate, fragile. The slightest interaction with the environment destroys entanglement through decoherence. You can't maintain entanglement across light years, let alone billions of light years, and definitely not across billions of years of cosmic evolution. unless the universe itself is entangled. Dr. Sharma proposed a radical idea. The impossible galaxies aren't separate objects. They're manifestations of a single quantum state stretched across space and time. The universe, at least in its early epochs, existed as one vast entangled system. The galaxies we see are localized expressions of a non-local quantum entity. This would explain all the anomalies. The temperature paradoxes arise because the galaxies don't have definite local temperatures. Temperature is a property of the universal quantum state, not individual objects. The quantum ghosts flicker because they're in superposition with other regions of space-time. They're both here and there, now and then. The retrocausality occurs because past and future are entangled. The temporal memory galaxies show future chemistry because the future state is part of the present quantum state, and the simulation-like patterns emerge because the universe is computing itself. Each observation collapsing the cosmic wave function, rendering reality from quantum possibility. But this raises the ultimate question: who or what is doing the observing? In quantum mechanics, observation causes collapse. An electron in superposition becomes definite when measured. But what counts as an observation? Traditionally, physicists avoided this question. Observation was pragmatically defined as any interaction that reveals information. But if the universe is a quantum system, something must observe it to make it real. Dr. Sharma's answer: the universe observes itself. Consciousness, or something like it, might be a fundamental property of certain quantum systems. When a system becomes sufficiently complex and integrated, it develops the ability to observe its own quantum state. The universe, through billions of years of evolution, became self-aware, and that self-awareness collapsed its own wave function, transforming quantum possibility into classical reality. We're not separate observers looking at the universe. We're the universe observing itself. Every conscious being, every brain complex enough to form observations, is a locus where the universe examines its own quantum state and collapses it into actuality. Though impossible galaxies are glimpses of the universe, before it fully observed itself, before consciousness evolved, before self-observation collapsed the cosmic wave function, we're seeing quantum reality. The universe as it existed when it was still in superposition, still probabilistic, still undefined. And here's the truly mind-bending implication: observation creates the past. When we look at distant galaxies, we're not seeing them as they were. We're causing them to have been. Our observation reaches backward through time, collapsing the quantum state of the early universe, determining which history actually occurred. The past is being written now, by observers in the present. This is called the participatory universe. Physicist John Wheeler's idea that observation doesn't just reveal reality, it creates it. Wheeler proposed a thought experiment. Imagine the universe as a quantum system that remains in superposition until observed. When conscious observers evolve and look back at cosmic history, their observations collapse the wave function retroactively, determining which history actually happened. The universe creates observers. Observers create the universe's history. It's a self-consistent loop, reality bootstrapping itself into existence. Webb's observations of impossible galaxies might be exactly this process in action. We're seeing the moment of collapse, the transition from quantum superposition to classical definiteness. Some galaxies have fully collapsed. They show normal physics. Others are still partially in superposition. They show quantum behavior at macroscopic scales. And a few are in transition, showing properties from multiple timelines simultaneously, as the cosmic wave function hasn't fully decided which history to manifest. Dr. Sharma's team developed a mathematical framework. They modeled the universe as a single quantum state undergoing continuous collapse due to self-observation. The the model predicted exactly the correlations observed. The entanglement between distant galaxies, the retrocausality, the quantum ghosts. It predicted something else. As the universe evolves and consciousness becomes more widespread, the rate of collapse should increase. More observers mean more observation. More observation means faster collapse from quantum to classical. The early universe, with no observers, remained quantum for longer, hence the abundance of impossible galaxies at high redshift. As stars formed, planets emerged, and eventually life arose, observation increased. The universe became progressively more classical. By the present epoch, quantum behavior is confined to microscopic scales, exactly what we observe. The model made a testable prediction. If we observe the universe more intensely, looking deeper, with better instruments, making more measurements, we should see the collapse accelerate. More observations should mean fewer quantum anomalies. We'd be forcing the universe to choose definite states. Dr. Sharma checked. Compared early Webb data to recent observations. The number of quantum ghost galaxies was decreasing. Objects that flickered in and out of existence in 2024 had stabilized by 2025, as if our observation was forcing them to choose, exist or not exist. Temperature paradoxes were becoming less severe. The mismatches between different temperature measurements were shrinking. Even the retrocausality was fading. Temporal memory galaxies showed weaker future chemistry signals in recent data. The universe was becoming more classical in response to our observation. We weren't discovering reality. We were creating it, and that meant something profound. The laws of physics aren't external rules governing the universe. They're regularities that emerge from the universe observing itself. Quantum mechanics, relativity, thermodynamics, they're not fundamental. They're statistical patterns in the cosmic self-observation process. In the early universe, with minimal self-observation, those patterns hadn't fully formed. Physics was fluid, flexible, probabilistic. As observation increased, the patterns stabilized. The laws crystallized. Reality became consistent. We're living in the era when the universe has mostly decided what it is, but traces of the quantum beginning remain. And Webb found them. And hidden in those traces is something that suggests we're not at the end of this story, but at the very beginning. By August 2025, research teams worldwide were analyzing Webb's impossible galaxies from every angle. And then Dr. Marcus Chen, a cryptographer at MIT, noticed something no astronomer had seen. The anomalies weren't random. They were organized. Like a message, Marcus had been helping his sister Sarah understand the data patterns when he recognized something familiar. The geometric progressions, the correlations, the distributions of anomalies across the sky. They looked like information in coding. He applied cryptographic analysis tools to the dataset, treated the anomalies as a signal buried in noise, and found structure. The temperature deviations, when plotted in sequence across multiple galaxies, formed a mathematical pattern. Not just any pattern, a prime number sequence. 2, 3, 5, 7, 11, 13, 17, 19, 23. Primes are the universal signature of intelligence. They don't occur naturally in physical processes. Finding them in the anomaly data meant one thing. Someone put them there. Marcus expanded the analysis. The quantum flickering patterns, when translated into binary, flickering equals 1, stable equals 0, produced another sequence. The Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13, 21. The redshift variations encoded p to 15 decimal places. These weren't random quantum fluctuations or simulation glitches. They were deliberate, intentional, designed to be found. The Chen siblings, Sarah and Marcus, worked frantically to decode the full message. They recruited linguists, mathematicians, cryptographers, computer scientists. Over 3 weeks, they extracted patterns from all 50-plus impossible galaxies. The patterns formed a coherent structure, a message with multiple layers. Mathematical universals came first. Fundamental constants, P. Euler's number, the golden ratio, Planck's constant, the fine structure constant. These established a common mathematical framework, proof that the message creators understood the same mathematics we do. Next came physical information, descriptions of atomic structure, the periodic table, nuclear physics, general relativity equations, but with differences, subtle modifications to the constants, alternative formulations of the laws. It was physics, but not our physics, physics from somewhere else. Then cosmological data, star maps, galaxy distributions, large-scale structure, but again, different from our universe. Constellations that don't match our sky, galaxy clusters in configurations we don't see. It was a description of another universe. Finally, the core message. Marcus and his team spent days on this layer. The encoding was sophisticated, using multi-dimensional data structures, but eventually they cracked it. The message read, "You are the first. The pattern continues. When you observe, you create. What you create creates you. The loop closes. The universe awakens. Welcome to the network." Sarah stared at the decoded message for hours. The implications were staggering. "You are the first," suggested we're the first civilization in our universe to reach this level of observational capability. The first to see the quantum foundations of reality. The pattern continues implied this has happened before, in other universes, other iterations. When you observe, you create, confirmed Dr. Sharma's participatory universe theory. Observation literally creates reality. What you create creates you, suggested a loop. We create the universe by observing it. The universe creates us through its evolution. We're both cause and effect. The loop closes might mean the universe is self-consistent. A closed causal loop where observation reaches backward to create the past that led to the observers. The universe awakens suggested consciousness emerging, the universe becoming self-aware through its observers. Welcome to the network implied connection to something larger. Other universes? Other conscious systems? But who sent the message? The encoding was buried in the fundamental structure of the early universe. It wasn't added recently. It had been there since the beginning, waiting to be discovered. Only one entity could have placed a message in the initial conditions of the universe. Whoever or whatever created the universe. If we're in a simulation, the simulators left us a message. If the universe is self-creating through observation, the message might be from the future, from the universe's fully evolved state, sending guidance backward to its younger self. If multiple universes exist in a larger multiverse, the message might be from other universes that reached this stage before us. The team discovered more. Hidden in the data were instructions. Instructions for building something. A device, a machine, a portal. The specifications were encoded in quantum states, geometric configurations, mathematical relationships between the anomalies. It would require technology we don't have yet. Quantum computers far beyond our current capability. Manipulation of space-time on scales we can barely imagine. But it was buildable. Given time, decades, perhaps a century, we could construct it. And what would it do? The instructions suggested it would amplify quantum entanglement, create a macroscopic superposition, link conscious observers across space and time. It would let us join the network. Dr. Sharma, reviewing the plans, realized what it was. It's a consciousness amplifier. It takes the quantum entanglement we suspect links all conscious beings and strengthens it, extends it. We'd become linked, not just humans, any conscious entities in our universe. We'd form a unified field of awareness, and that unified field could observe the universe at a level we can't achieve alone. We'd collapse the cosmic wave function collectively, determining reality through consensus. Sarah Chen added, and if the network extends beyond our universe, we'd be joining something vast, a coalition of conscious universes, each one observing, creating, influencing the others. We'd be part of a multiverse democracy, reality determined by collective observation across all universes. The implications were beyond comprehension. Everything we thought about consciousness, reality, and our place in the cosmos would change. We're not isolated observers in a dead universe. We're participants in a living, self-creating, interconnected cosmic system. The universe doesn't just exist. It thinks. It observes itself. It evolves toward greater self-awareness. And we, conscious beings arising from matter and energy, are the universe's way of knowing itself. Every observation we make writes the past. Every thought we think shapes reality. Every discovery brings the universe closer to full self-awareness. The impossible galaxies Webb photographed aren't anomalies. They're invitations. Invitations to recognize our role. Invitations to join the network. Invitations to participate in the universe's awakening. And as you drift toward sleep tonight, consider this. You're not just observing reality. You're creating it. By September 2025, the full message and its implications had been shared with world governments, scientific institutions, and eventually, the public. Reactions varied wildly. Some saw it as proof of divine creation, God leaving a message in the cosmos. Others saw it as confirmation of the simulation hypothesis, our creators making contact. Many saw it as Dr. Sharma did, evidence that consciousness is fundamental to reality, and we're approaching the moment when our universe fully awakens to itself. Work began on the device. International collaboration. Funding from dozens of nations. The greatest engineering project in human history. Estimated completion, 2075. In 50 years, we'll activate it. Join the network. Become full participants in the cosmic dance of observation and creation. And the universe, our universe, will take its place among the multitude of conscious, self-observing realities. But the changes started immediately. The discoveries didn't just affect physics, they transformed everything. Philosophy grappled with new questions. If observation creates reality, what is the nature of existence before observation? The answer seemed clear. There is no reality without observation. The universe exists because it observes itself. Existence and consciousness are inseparable. Religion faced upheaval. Some traditions embraced the discoveries. The idea that consciousness creates reality aligned with certain Eastern philosophies, the concept that mind and cosmos are one. Others struggled. If the universe is self-creating through observation, where does God fit? New theologies emerged. God not as external creator, but as the cosmos knowing itself. The network as divine unity, psychology and neuroscience shifted dramatically. If individual consciousness participates in creating reality, then the mind isn't passive. It's an active agent determining what exists. Studies began exploring how beliefs and expectations might literally shape reality at quantum scales. Placebo effects, mind-matter interaction, phenomena previously dismissed became serious research areas. The message's instruction, when you observe, you create, wasn't just cosmic. It was personal. Each person, through their consciousness, participated in creating their experienced reality. Technology development accelerated. The consciousness amplifier became the focus of international effort. But other technologies emerged too. Quantum computers designed to manipulate observation-dependent reality. Meditation chambers enhancing quantum entanglement between minds. Devices letting people consciously collapse wave functions. Early results were promising. Connected groups of meditators showed measurably increased quantum coherence. Their brain waves synchronized. More remarkably, Physical systems near them showed reduced quantum noise, as if collective observation stabilized reality more effectively. This led to practical applications. Quantum computers near meditation groups performed better. Chemical reactions in observed systems proceeded more efficiently. Medical treatments improved when patients and doctors collectively observed and intended healing. The boundary between mind and matter was dissolving. Society itself began to change. If consciousness creates reality, and we're all connected through quantum entanglement, then the collective consciousness of humanity shapes our shared world. Social movements emerged around conscious reality creation. Groups focused on collective observation of desired outcomes: peace, environmental healing, technological breakthrough. Skeptics remained. Hard-nosed materialists who insisted the Webb discoveries were misinterpreted, that the anomalies had mundane explanations, that the message was pattern-seeking in randomness, but the evidence kept mounting. More impossible galaxies, more encoded information, more predictions from the message that proved accurate. By 2030, the skeptics were a minority. The world had accepted the new paradigm. We live in a participatory universe. Reality emerges from observation, and consciousness is fundamental. Education systems restructured. Children learned observation meditation alongside mathematics. The ability to consciously participate in reality creation became as essential as literacy. Reality studies became core curriculum. Students practiced quantum observation, studied the ethics of conscious creation, learned to recognize and navigate the network because that's what the discoveries ultimately pointed toward. We're not alone. Every conscious being in every universe is connected through the network, and as we develop our observational capabilities, we'll become aware of that connection. First contact wouldn't come from radio signals or visiting spacecraft. It would come from consciousness, touching consciousness across the quantum network. Some people claimed it was already happening. Mystics and meditators reporting contact with other minds, not human, not even from our universe, but real nonetheless. They described beings of pure observation, entities that exist as patterns in the cosmic wave function, consciousnesses older than our universe, from realities with different physics. The network wasn't empty. We were joining a community. Dr. Sharma, now leading the Consciousness Amplifier project, reflected on the journey. We pointed Webb at the sky to photograph distant galaxies. We thought we were doing astronomy. Instead, we discovered the universe is alive, conscious, self-creating. We found that we're not observers of reality, but participants in its creation. Every thought matters. Every observation shapes what exists. And we found we're not alone. There's a network of conscious entities across the multiverse, all observing, all creating, all interconnected. When we activate the amplifier in 2075, we won't just be joining that network. We'll be consciously, deliberately stepping into our role as co-creators of reality. Humanity will graduate from unconscious participation to conscious participation, from accidentally shaping reality to intentionally guiding it. We'll take responsibility for what we create. The ethical implications were staggering. If observation creates reality, then observers bear responsibility for what they create. War, poverty, environmental destruction, if these exist partly because we observe and thus create them, then we have the power and obligation to observe differently, to create a better reality. Global councils formed to discuss collective observation ethics. What should humanity focus its collective consciousness on? What reality should we create together? Some argued for utopian visions, peace, abundance, harmony. Others warned against imposing one group's vision on all of reality. The network's message suggested diversity, each universe contributing its unique observation to the multiversal whole. Perhaps our role was to create and observe uniquely human realities, our contribution to the cosmic tapestry. By 2040, meditation centers were as common as gyms. Collective observation sessions happened in schools, workplaces, communities. Crime rates dropped. Environmental restoration accelerated. The impossible had become normal, and everyone knew. This was just the beginning. When the consciousness amplifier activated in 2075, everything would change again. We'd join the network fully, access the collective observation of countless conscious civilizations across infinite universes. We'd see reality from every perspective simultaneously, understand physics not just in our universe but across all possible physics. We'd become truly cosmic beings. The impossible galaxies Webb photographed were a threshold, a doorway opening, an invitation we couldn't refuse. The universe was waking up, and it was calling us to wake up with it. As you close your eyes tonight, know that your consciousness is part of something vast. You're not separate from the universe. You're how the universe knows itself. Sleep well, cosmic creator. Tomorrow, you'll wake up and create reality again. If this journey through impossible physics and cosmic consciousness moved you, subscribe. Every week, we explore the universe's deepest mysteries, from black holes to quantum realms, from distant galaxies to the nature of mind itself, all designed to expand your consciousness as you drift into sleep. Sweet dreams, reality creator. And remember, you're not just in the universe. You are the universe, experiencing itself.